Hello everyone. We're excited to be sharing with you some of the most recent advances in the applications of reinforcement learning to recommendation systems. In particular, we're going to be giving a high-level overview of the techniques described in Google's recent SlateQ up paper, then a comparison of the performance of that algorithm to other more traditional reinforcement learning approaches. We find the SlateQ algorithm so interesting because up to this point, reinforcement learning has not had much success in optimizing recommendation systems. In practice, most RL agents working in the recommendation environment focus on optimizing the user's immediate response to the recommended item. In other words, they are very greedy, optimizing for short-term rewards. In most toy situations, this can work okay, but in recommendation systems, there are very non-trivial trade-offs associated with the short-term and long-term responses of the user. This, of course, is no secret. The reason that most RL attempts have ignored these long-term effects is because they're notoriously difficult to model. In the typical recommendation setting, there are an incredible amount of both users and candidate items to recommend. As a result, exploration of that action space is nearly always intractable. Let's be a bit more specific. Modern recommendation systems require selecting a slate of, say, K ranked items out of a pool of L total items. If, for example, you have 20 candidate items and 10 that you'd like to recommend, then there are over 670 billion combinations of items that could be recommended. By nearly any scale, this is a minuscule recommendation system, and still it just would not be possible to explore that type of action space, at least not in any meaningful way. This is the problem that the SlateQ algorithm attempts to solve. Its solution proposes the introduction of a few simplifying assumptions whose bounds are fairly innocuous and reasonably match our mental model of reality. The first assumption states that rewards associated with any given slate of items only depends on the item that was selected. This is not true in reality, of course. The reward is somewhat dependent on all items that were made available to the user, but this enables us to decompose Q values associated with each slate into Q values for each item, a far more useful quantity. The equation expresses the same notion, but in math. The second assumption is that the behavior of the user follows a multinomial logit user choice model. While somewhat more restrictive, this assumption makes the TD update computation possible, without which training an RL agent simply wouldn't be an option. Now that we have a solid intuition of what the SlateQ algorithm is trying to do, I want to explain how all the pieces fit together. The state of our environment consists of a set of features describing the given user. Given these features about the user, the agent's actions consist of selecting and ranking K possible items, or documents in this diagram, that make up the state that is recommended to the user. The slate that is recommended to the user. Finally, the rewards are simply the immediate engagement of the user with one of the recommended items, or the lack of engagement. The observable features about a user are simply an n-dimensional vector representing characteristics about the user. These could be things like their browsing history, demographic, or geographical features. Each candidate item additionally is represented as an n-dimensional vector, and these things most likely are describing the content about that item. Finally, the rewards here are composed of the user's response, which we measure in multiple ways. Our system records whether or not the user clicked on the recommended item, which category the item came from, how long they interacted with the item, whether or not they liked it, and the quality of that given item. We ran our experiments with a pool of 10 total items and recommended 2 at each time step. So with this system in place, we can simulate episodes in a recommendation system and evaluate the SlateQ approach against similar RL approaches. In our experiments, we employed what's referred to as the full SlateQ learning algorithm, which attempts to learn Q values for each of the exponentially exploding possible actions. This technique is known to be a myopic decision maker, optimizing for short-term rewards. The first metric we were interested in is the average rewards per episode. We can see that both the SlateQ algorithm on the left and the full slate algorithm on the right show much variance. After training each model for about 800 iterations, we see that the SlateQ algorithm settles on an average reward of about 158 per episode. The traditional full slate algorithm, on the other hand, lands at 149. Given the greedy nature of the full slate algorithm, our expectation is that this disparity would continue to grow if trained for more iterations. The second metric we chose to evaluate is one that's familiar in this space, click-through rate. We see again that there's quite a bit of variance in both algorithms. The SlateQ on the left again notches the traditional algorithm, boasting a click-through rate of 0.5 as opposed to the CTR of 0.48 on the right-hand side. And again, with larger iterations of training, we would expect this disparity to grow. But even on this 800 iteration timeline, a 2% difference in click-through rate may not seem like that much. It's important to remember, however, in large companies who serve recommendations at the scale of, say, Google, a 2% difference in click-through rate can increase revenue by millions of dollars. In this presentation, we've delineated the details of the SlateQ algorithm for applying tractable reinforcement learning to recommendation systems. The novelty of this approach involves the utility of two assumptions, one of them about the rewards and the other about the state, which simplify the learning computation and allows us to efficiently estimate the long-term value of individual items in the system. We've empirically shown that the SlateQ algorithm outperforms traditional Q learning in this difficult task when it comes to both average rewards per episode and click-through rate. This research sheds light on exciting applications of reinforcement learning in recommendation systems and paves a path towards training efficient, scalable agents with the use of domain-specific model-based approaches. Thank you.